Okay, welcome back to another lecture for Physics 325 Remote Edition. Last time we talked about imaging systems. We looked at what an imaging system was, namely a mapping of points to points. And we looked at two different types. There was the zero lens system, which we called a pinhole camera. And we looked at a single lens imager, a very simple imaging system as well. We're actually going to consider that to be a particular type of imaging system called a simple magnifier or magnifying glass. And that's great. And that allowed us to find out where images were formed. You can even find out how big they are. I haven't gone into too much detail yet, but it's fairly simple. What happens when we get something that looks like this? That's what our goal is today, to try to figure out how to do and how to treat something like this. So let's look for an n greater than or equal to 2 lens. If n is equal to 2, we're going to see a few examples, namely a compound microscope and a Galilean telescope that are very important and important to study. But when you look at a real imaging system that's in a fancy optical element, it's going to look more like this beast here with its myriad lenses. So let's think about how to deal with that. We're going to look at what happens to a ray. And remember, a ray is a representation of a particular plane wave. So we're going to look at what happens to a ray as it propagates through the system. Let's take a random ray and a random plane wave, therefore, and it's going to propagate through the system. And I'm just going to roughly kind of trace it by eye what should happen. It's going to do something like that. An array at a different angle is going to do something else. So that's pretty intimidating when you first see it. However, what we're going to deal with today is we're going to develop a method to replace this entire thing today. We're going to replace this entire beast with 4 numbers, namely a 2x2 matrix. And then ray tracing is a breeze. We just plug in whatever ray we want coming in, and we're immediately going to be able to spit out the answer with a couple multiplications and additions. It's a very powerful method known as matrix ray tracing. At least that's what I call it. I don't know if that's the official term, but it is now. I'm officially declaring the official term for what we're going to develop, matrix ray tracing. So let's break this down to its fundamental, physics, the fundamental physics of what's happening every time we look at this system. So let's draw like a generic surface. And what we have here is we have index 1 on one side, index and 2 on the other side, and they're separated by the interface, between them is some surface with some radius of curvature. And there's really only 2 things that can happen here. There's only 2 things we need to consider. So let's just look at a particular ray. I'm just going to invent one. It starts around the origin there, hits a surface, and then goes Let's really think about what this ray is. Remember, the ray is just a representation of a plane wave. How do we specify it? What do we need to specify it in this 2-dimensional picture? Of course, we live in 3-dimensional space, but what we're representing here is something that's rotationally symmetric. So we have angles and a situation which is symmetric about the z-axis. What do we need in order to specify this ray? Well, it's a line. So we need 2 points, or equivalently, we need a point and a slope. So we have some angle incoming with respect to the x-axis, is going at some angle, and it initially is striking the surface at some height, h1. And then when it hits this refracting surface, it changes angles, so that its angle with respect to the horizontal is now alpha 2. And that's what a refracting surface does. it changes the angles. But remember, there's two numbers that we need to keep track of. There's the height as well. We need a point as well as an angle. So how do we change heights? Well, that's just free propagation. So it's going to go somewhere else, and somewhere down the line, it's now at a different height. So basically, we can completely characterize what happens to an optical element by keeping track of the height and the angle, and what changes those are propagation and refraction. So to be clear, there's two things that can happen. Thing one, refraction. And in this case, it happens at a point, so the heights are unchanged. And the other thing that can happen is we can change height via propagation, so that we don't change the angle, that stays the same, but we change heights. Now the amount that it changes, of course, is dependent on the angle, but the angle itself is unchanging. So that's it. Keeping track of the height and the angles at all points in space tells us everything about the ray, and how they transform tells us what the optical system is actually doing. So we need to only look at these two things, and we're going to shove them together in a vector. We're going to define a ray vector as follows. At a given point, our ray is going to be equal to the index, we have the angle, and we have the height, which is the height above the z-axis. And I should be more specific with the angle. It's the angle with respect to the horizontal. And that's it. So everything we do, which we've just said is either propagation or refraction, is really transferring one ray to another ray. And that's basically a two-dimensional vector to another two-dimensional vector. And we're going to restrict ourselves to things that are linear. Refraction, Snell's law, in the paraxial approximation turns out to be linear, and straight propagation is linear. Anytime we have a linear mapping, we can represent between these two-dimensional vectors, we can represent that as a 2x2 matrix. So we're going to look for a matrix to map the two. This is exactly the same kind of reasoning as we used to simplify things with the Jones vectors when we did polarization. And we're just going to get a new angle. Perhaps we're in a new medium, so a new index and a new height after propagation. And what we'll do now is just try to figure out what these are. So this is really, what we're going to do now is try to derive these two matrices which we need, which are propagation and refraction. And the picture will look something like this. Effectively, what we're going to find is that everything is propagation and refraction. So this complicated, crazy system here, let's try to think about, just to pay it forward a bit, what are we actually going to look for? Well, we're going to have a refraction, followed by a propagation, followed by refraction, followed by a propagation, followed by refraction, followed by a propagation, etc., all the way down the line. And each one of those is a 2x2 matrix. If you multiply 1,000 2x2 matrices together, your answer is a 2x2 matrix. That's what we're going to do. So let's go about working out what some of those matrices are. There's only two of them. Let's start with maybe the easier one, which is propagation. So let's try to derive the propagation matrix. So what is this thing going to do? So let's first draw that out. So we're going to have a ray coming in at some height. and it's going to move to some other height. And it's going to be at some fixed angle alpha with respect to the horizontal. So let's write down what this matrix is going to do. Just from geometry, we have tan of alpha is going to be equal to rise over run. That's a slope. And I guess we should give it a label. How far does it go? Let's call that D. Let's try to rearrange this. H2 is equal to, that's what H2 is going to go to, and alpha, of course, is just going to stay alpha. So that means what we want is the following matrix. I've just decided we're working in the paraxial approximation. So why am I wasting these 3 letters and writing tan alpha? Tan alpha is about equal to alpha. Yeah, that's going to make things a lot easier. So it's going to be H1 plus D times alpha. But that's also equal to some as yet unknown 2 by 2 matrix times the original input vector. So let's think about this. If we apply the first, if we look at the way matrix multiplication works, the first element is equal to, is multiplied rather by the first element of the vector. So A11 or T11 is multiplied by n alpha, and this is multiplied by that, and we add them together. We have n alpha times 1 plus h times 0 is really what we want. So this should be 1, and this should be a 0. Now, how about the second one? Well, we see that we do have an alpha, so we'd like to multiply this term here by something such that we get d alpha plus h1. So just brute forcing it, really. We'll set this to d over n. And that also will get added to this element times h1. And we'll just see that that should be a 1. So this here is our translation matrix. That's T. So our propagation is described by a 2 by 2 matrix. We'll call it TD. Translation for over a distance d is equal to 1, 0, d over n, 1. And just as a quick sanity check, let's see what happens when we have translation with length 1 meter followed by translation with length 2 meters. We should get a translation matrix equal to 3 meters, right? Translation should add. Let's verify that. Let's have a quick look. So if we take the product of these two matrices, we'll get 1, 0, d1 over n, 1, 0, d2 over n. And what is that? Well, this first component here is going to give me 1, 0, 0, 1, so that'll be a 1. The second component will be 1 times 0 plus 0 times 1. Was that right? Yeah, 1 times 0 plus 0 times 1, so that'll be a 0. The third component is going to give us d1 over n times 1 plus 1 times d2 over n, which is looking pretty good, because that's going to give us d1 plus d2 over n. And the second component is 0 times d1 over n. So it's 0 plus 1 times 1. And that'll give us a big fat 1. And this is just a translation for a total distance of d1 plus d2. Great. So it's believable, at least. So that is a matrix that describes propagation over a distance d by a ray. It gives us a new height, and that's it. Okay, I feel like we had to do one more. Yes, we had to do refraction. So refraction, the math is a bit more of a pain. So I'm going to have to whip out a pre-made diagram. Let's do that. So this is the setup that we need in order to derive what the refraction matrix does. Again, we have a beam coming in at angle alpha 1 here, which is the same as that alpha 1. And it's hitting the lens at the surface, rather, at some height. So what can we do here? Effectively, we know what happens when we have interface between two indices of refraction. We have refraction, and that is Snell's law. And all this complicated geometry is a way to get the normal vector. Because remember what Snell's law tells us. So Snell's law told us that n1 sine theta 1 is equal to n2 sine theta 2. And we're going to be very lazy because we're in the paraxial approximation. And paraxial Snell's law is even easier. Small angle approximation. Sine theta is approximately equal to theta. So it told us that n1 theta 1 is equal to n2 theta 2. But theta, what is theta? Remember, theta is the angle that the beam comes in with respect to the normal to the surface. So here, that is beta plus alpha. All right, so let's try to work out this. So here, theta 1 is beta plus alpha 1. Okay, how about on the other side? Well, we have this angle beta here. Beta is the angle from the center of the sphere. Remember, this is a spherical surface, radius r. The center of the sphere to where the beam hits. That's what gave us our beta. So our theta t here is equal to alpha 2 plus, and if we can look at it just the right way and use one law of geometry, we see that that's also beta on this side, so that theta 2 is equal to beta plus alpha 2. All right, and now that we know theta 1 and theta 2, we can use the paraxial Snell's law. From this geometry here, we have a triangle with the tan of beta, which is approximately equal to beta, equal to h over r. Again, r is the radius of curvature of this surface here. So that pretty much gets us almost to where we want to go. Let's use Snell's law now. Snell now says, what does our friend Snell say? n1 theta 1 equals n1 h over r plus n1 alpha 1 is equal to n2 h over r plus n2 alpha 2. n2 alpha 2 is equal to n1 alpha 1 plus, what is this going to be? It's going to be n1 minus n2 h over r. So let's try to reformulate that into a matrix equation. So again, we're going to have the heights are the same. Remember, we're going like an infinitesimal distance just across the surface here. So let's write R2 is equal to n1 alpha 1 plus, let's write it in this suggestive way, n2 minus n1 h over r. H is equal to again, blank, 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 times my input vector, which was n1 alpha 1 h. Okay, so let's try to fill in the blanks here. So if we look at the way matrix multiplication works, we're going to multiply this by this, and then this by this to get the first one. So we can already see from multiplying the 1, 1 component of there, this should be a 1, because we have that n1 alpha over here. And what do we have to do to get negative n2 minus n1 times h over r? What do we have to multiply h with? Well, we're going to need a bigger box here. Negative n2 minus n1 over r. And for the second matrix multiplication, we want whatever goes here times n1 alpha 1 plus whatever goes here times h to be equal to h. And by inspection, we can see that should be a 0 and a 1. So this is our matrix. This is our matrix for refraction. Excellent. We can go a bit further, actually. So we might have recalled from our earlier analysis of lenses that we had this number, the focal length, and we called it n minus 1 over r. And we can actually, we didn't write it this way, but we can generalize this. This is for air to glass. If we want to go n2, or rather n1, to n2, this is generalized as n2 minus n1 over r, and that is our focal length for a spherical surface. That's where all the rays converge to, or from. Nice. So this whole term here is 1 negative 1 over the focal length of that surface. And there's a word for 1 over the focal length. Just like there's a word for 1 over period, and frequency, and so on and so forth. There's a term that is represented by 1 over f, and that's called the strength of the lens, or the dioptric strength. And this is because if you have a very short focal length, you have a stronger lens, right? What does that look like? If I have a lens like this, if I have a lens like this, and it focuses everything in a millimeter within the lens, that's a very strong lens. Or if I have a puny lens like this, if I have a lens like this, that focuses like way far away, that's a weak lens. So the smaller f, the stronger the lens. So we sometimes call one over f, the dioptric strength. That's how strong of a focuser you have. And the units are diopters. One diopter is 1 over 1 meter. Okay, so with d is equal to 1 over f, we can finally write the refraction of a lens, or rather just a single curved surface, as 1, negative d, 0, 1. And why do we use dioptric strength? What's so useful about dioptric strength? Well, let's suppose that we have a few curved surfaces with no propagation between them, just one after the other. If we have two refractions, we have two curved surfaces right next to one another. What do we get? We get, it's performing that matrix multiplication, negative d2 minus d1. What we find is that dioptric strengths add. So when you have two lenses with each having a focal length of, say, 100 centimeters, and you put them together, the focal lengths don't add. You don't have a weaker lens, i.e. one with a 200 centimeter focus. You have a stronger lens. namely you have a 50 centimeter lens. I'm getting a call, and we'll pause the video. Okay, I took that very important phone call. So, where was I? Yeah, dioptic strengths add. So it turns out with these two matrices that we have, we already can solve that crazy complicated system here. If we know the radii of curvatures, we can immediately get the focal lengths and therefore the dioptric strength of each one of these surfaces. If we know the lens thickness of these crazy lenses, well, we can get the translation matrices, and we just mash them together, and we're going to get some matrix. I don't know, 0.75, 2.8, negative 3, 2.7. I just made those numbers up, but it's going to be some set of numbers, and that means that we don't have to recalculate it for every ray. Every ray, we just input the two numbers, alpha and h, that determine the ray, and just grind them through that 2x2 matrix, which is a very simple operation. And that tells us upon exit what the height and the angle will be. Okay, so we've done all this heavy lifting to derive two matrices, the refraction matrix and the translation. But this is really like gold here, because with these two matrices we can basically derive the effect of any optical system. But there's one more kind of piece of red tape we need to cover first, and that is a sign convention. Sign conventions are always annoying. So just for example, let's suppose we had this. Let's suppose we had a concave. Suppose we had a concave instead of a convex surface or curve. What would change in our analysis? I mean, we still have the same effect. We still have the basic idea where we have a ray coming in at a given angle and height. But now we look at our r. That's not where alpha should be. When we look at our r vector, it's on the negative side instead of the positive side. So our distance, when we do our geometry, is going to have the effect of replacing r with a negative r. And that's just because we're now on the other side of the lens compared to where our ray is coming in, and we did our rise over run. We're going to get a negative sign out. So that tells us now that f is going to go to n2 minus n1 over negative r, and effectively go into negative f. Negative f, what does that mean? Negative f if we had a convex rather. What does a negative f mean? Well, we can figure out what a negative f means just by looking at what we had with our spherical waves. So a negative f means that we're going away from a point that's to the left of the lens, or left of the surface. So f less than 0 describes something like this. We have a plane wave coming in, and we have rays that are also a spherical wave. Remember, we had our spherical wave. But they're coming away from a point that seems to happen before the lens. So the rays are exactly as if it had some origin before the lens. The rays act as if they're diverging from a point before the surface. Anytime we have that, we have an optical system which makes purely diverging rays. We have what's called a virtual image. What is a virtual image? It basically means that we cannot put a piece of paper up here. If we put our piece of paper like we did in the example yesterday right here, we will not see an image. All the points don't come together. All the rays, rather, do not come together at a point. We need an additional lens to project the image. So you cannot project a virtual image to a screen. However, you can see a virtual image. Why do you think that is? Well, you have a nice lens, a a couple of them, for the most part, attached to your head. You have lenses in your eyes. So you can actually see, as a human, you can see a virtual image, but only because you have an additional lens which is bringing those rays into focus. So a negative F means it creates a negative F will create a virtual image of a plane wave. There's many different ways of getting a virtual image, but a virtual image is whenever you have an optical system where on the output of that optical system, we are diverging from a point rather than converging to a point. Okay, great. So let's just enumerate our possibilities here. We had the original case we did, where we had R greater than 0. We had the case we just analyzed, which had that negative R. F was less than 0. How about the other way around? We flip the lens around, and we have a curved surface on the other side. Well, in this case, yeah, the radius is on the other side, but also the curvature is on the other side, but also we're going from a higher end to a less high end. So how do I say this? We're going now from n2 minus n1 is less than 0, and R is less than 0. And we have a double negative, so we have F greater than 0 as well. It's a combination. And finally, if we have a concave lens face the other way, again we have F less than 0. So a good way to remember it is concave. I like to think of that like a cave. It caves in. Will always lead to F, a negative focal length. And convex will lead to a positive focal length. Okay, so now that we have the sign conventions down, we've said what a virtual image is. Let's do 2 quick applications of this formalism. The first thing we can do is look at an entire system. So for example, let's look at the entire matrix of a thick lens. If we look at the entire matrix of a thick lens, we're going to get, let's look what we get. We have an incoming ray. We have R1, which leads to a dioptic strength. We have a thickness, D. And we have R2, which is some other dioptic strength. So the matrix that corresponds to a thick lens is given by L, thickness D. The first thing that the ray sees is the first matrix. So that's what we're going to want to hit it with first. And then we go through a translation, D over N. Translation D over N. And then we're going to finally, after that translation, hit the last surface. And that's going to be applied on some input vector, n alpha times h. And the reason it's in this order is, remember that we're going to first hit this, and then we're going to multiply the result of that with the translation, and then the result of that with the second surface. And that is the matrix that corresponds to a thin lens. I'll let you work out the details for that matrix multiplication, but you can write any thick lens this way, and it'll tell you how to incorporate the thickness. But we can also apply the matrix corresponding to a thin lens when we're going to look at multi-element systems. So a thin lens is merely one with d is equal to 0. So the thin lens is going to be given by 1 minus d2 times the identity matrix, because that lower left is a 0, times this here, which we've already seen. We can write that as 1 negative 1 over the total focal length and that is the matrix of a thin lens. And that's great. So, for example, let's suppose we have something like this, and we want to put in a ray. Let's just make let's look at this as an optical system here. That corresponds to some m. Well, that's going to merely be the lens matrix corresponding to negative 40. Let's just write it down. Times 10 centimeters. Let's say this is air in between. We're going to have 0 d over n, so that's going to be a 10. And finally, negative 1 over 20. And we can blast that away and see what this lens system does. So why not? Let's just grind through it. Hopefully it's not a total mess. Maybe it is. So we're going to get 1 plus 10 over 40. That's 1/4. So that's going to be 5/4 in this element times 1 over 40. And we're going to get a 10 here, and a 1, times, we've got to times it by the original thing. I should never make up numbers on the spot. Let's see if we get a total disaster. We're going to get 5/4, that's 1.25. Is that, yeah, times 0. Here we're going to get 5/4 times negative 20 minus a 40th. Oh, heavens. All right, let's see what we get here. So we're going to get negative 5 over 80 plus 1/40th, which is 2 over 80. So we're going to get 2 over 80 minus 5 over 80. Could be worse. Here we get a 10 again. And what do we got here? Negative 10 over 20, which is negative 0.5, plus 1, which is 0.5. So our lens, oh boy, is let's just write it out. 1.25. I'm going to leave this as negative 3 over 80 because I can't do math. And what do we get? 10. 0.5. Okay, so that is our matrix corresponding to this thing here. Finally, we're going to do one last thing. We're going to see where the focal length of this thing is, see where a focus comes in. Okay, so let's actually see what this tells us about the effective focal length of the system. So the effective focal length of a system is just pretending this whole optical system, treating this whole optical system as just one abstract unit, like a lens. We send in a collimated beam, and we see where it focuses. So collimated means perpendicular to the axis. It's going to emerge at some, in general, different height, and at some different angle. And where it crosses the z-axis, that's the effective focal length here. And we see that it focuses if that alpha is negative, if that angle with respect to the horizontal is negative. So we can look at this very abstractly. What does it look like to send in a parallel ray? Sending in a parallel ray means that alpha is equal to 0. And at the outset, on the other side, we have our output ray is going to be n times alpha h2. And if we look at the triangle this makes, tan of negative tan of alpha, is equal to h over f, negative h over f. So that's approximately equal to alpha equals negative h2 over f. right? Because this angle is negative now. So the rise is negative when we do the rise over run formula. Okay, so that's what we're going to get in general. But let's look at that in terms of the matrix picture. So if we have a collimated input beam, and we plug it into some ABCD matrix, 0H, that's going to be equal to, if we just grind through the math, just the B component and the D component times H. Let's see what we get here. That should be equal to N alpha 2 over H. So over B times H, and I guess there should be an N there too. Where's that N going to come into? I have to think about that. There's really H2 over N alpha, alpha over N. So there should be an N up here too, because it's really like B over N is equal to alpha 2. And these H's cancel out. So this is actually F is equal to negative N D over B. Okay, and that's what that tells us. So in our case here, let's move to our example from here. We have that the effective focal length is equal to, let's just say N is equal to 1, we're in air, negative D over B. So that's 1 negative 1/2 over negative 3 over 80. So that is 80 over 6 or 40 over 3. And that is the effective focal length. So we can actually draw that. Let's move it up to our example here. We can see what happens here. We can actually do a ray trace. So it started at some height. Let's just, it's 1, whatever it is, 1 times H. And this tells us that by the time it gets to the other lens, it's at 1/2. Right? That's what this tells us. And then it gets deflected such that the distance 40 over 3, what's 40 over 3? About 13.3. Repeating. 40 over 3, 13.3. So this distance is 10 centimeters. It goes even further than that distance. We're going to have to back this up to make some room here, because this kind of tapers off the angle. So it goes a bit even further, and it goes a distance an additional 13 centimeters this way. So it's 23 centimeters from the front and 13 centimeters from the back, and that's what this lens does. We could do this for any number of rays. So we could plug this into a program and find it, but this is how you use the matrix method for tracing any ray. In fact, let's have a quick look at that. Okay, so after waiting the approximate 7 years for Jupyter Notebook to load up, or Jupyter Lab to load up on my laptop, I've clobbered it. I've written a very quick and dirty Python program, which basically just defines these matrices, refraction, transmission, thick lens, and thin lens. This is just the way you write matrices, or the way I do in Python. There's probably a better way to do it for those of you that actually know how to program. And what this does is it just simulates propagation. So we're going to start it just to show a collimated beam coming in. We're going to propagate for a bit, hit the first lens, focal length of 20. And then we're going to hit a second lens with a focal length of negative 40, and then just propagate for a bit. Is that going to be enough? It may not. So let's go to 20 and see what we get here. So we propagate this all out, and this is what we get. So we have, apologies for not being a sweet, amazing Python coder, but I should have drawn lenses in here. But what we see here is we have a first lens. I don't know if you can see this mouse. At x equals 10, that's our new x equals 0. 10 centimeters later, we hit our second lens, and that diverts the beam a bit. 13 centimeters after that, it all converges, and this is what our imaging system looks like. So let's try this. Will this work? Let's see if this will work. It totally doesn't. Okay, give me one sec. Let's save the image temporarily. I know what I can do. I can use Microsoft's sweet screen clipping tool. Alright, good. So here's what we got. We have our first lens here. We have a diverging lens here. Yes, I know. I cannot draw. And this is effectively x equals 0. 10 centimeters later, we have this. And then 13.3 centimeters, we have our focus. And this is how you can simulate this thing. If we wanted to go just nuts, we could add some more lenses. Let's do that just for fun. Let's just see how easy it is. In fact, I could probably code this up a lot more efficiently. But let's add another lens in. Heck, let's add 2 more lenses in. 3 and 4. We'll make a strong converging lens. And we'll put it in, about 10 centimeters, and a weak diverging lens. Let's just give it another weak converging lens, 15 more centimeters down the line. And we'll go another 10 centimeters. That is just want to show how easy it is. That's what that looks like. Is that what's going on there? Let's do a quick little test. Sorry. I didn't actually define anything. That looked very similar. There we go. Oh, man. Not my day. Okay. Hey. And there's our new lens system. So we just have more lenses in here. Maybe when I have a bit more time, I'll get this program to draw lenses. But we can plug in Avogadro's number of lenses, and we're still going to get this thing simulating. So that's how you use this matrix formalism. And that's it for lecture 27. I'll talk to you for lecture 28.